Hi, hello. Welcome to my second class on nucleophilic substitution reactions. Nucleophilic substitution reactions. So, given our understanding about Sn2 reactions in the last class, if we were to measure the rate of reaction of tertiary butyl bromide with water, we would expect a relatively slow contribution reaction since water is a pure nucleophile and tertiary butyl bromide is sterically hindered to attack by a nucleophile. However, we actually discovered that reaction is surprisingly fast. It is in fact over our million times faster than the reaction of methyl bromide in a compound with no steric hindrance with water. So, clearly the reaction must be taking place by a mechanism different from that of Sn2 reaction. So, what is tertiary butyl bromide's nature in water when it is a poor nucleophile? So, as we have seen, a study of chemical kinetics of a reaction is one of the first step undertaken when investigating the mechanism of the reaction. If we were to investigate the kinetics of the reaction of tertiary butyl bromide with water, so what is tertiary butyl bromide? This is tertiary butyl bromide. This is nothing but tertiary butyl bromide. So, if it is unites with water, in a substitution nucleophilic reaction, then what is going to form? An alcohol definitely will be formed. Tertiary butyl alcohol. This is nothing but tertiary butyl alcohol. This is the tertiary butyl bromide. Tertiary butyl bromide. Plus, you know this Br is a leaving group that will become Br minus, and also water will be removed. Some water, some H plus ion will be removed. Okay, H plus ion will be removed. So here, what is the rate of reaction? What is the rate of reaction? Rate is given as directly proportional to the substrate. Substrate is nothing but alkyl halide. Alkyl halide or tertiary butyl bromide in this case. So, because of the rate of reaction depends upon the concentration of only one reactant, it is a first order reaction. An Sn1 reaction has two steps actually in this. The carbon halogen bond breaks down. Here this is carbon halogen bond which will breaks down heterolytically with the halogen retaining the previously shared electron pairs. In the second step, what will happen is the nucleophile, whatever is the nucleophile, reacts rapidly with the carbocation formed in the first step. So, what is the step 1 here? Step 1 is nothing but there is a formation of carbocation when carbon halogen bond separated out heterolytically. This fission is nothing but heterolytic fission. Heterolytic fission. Then we will get a carbocation. We get a carbocation. As you know, this is a carbon positively charged. So with 3 other alkyl groups, methyl groups, CH3. Here CH3. Here also CH3. Now Br minus went along with the bond pair of electrons present in the alkyl halide. So this is our leaving group, and this is the carbocation. This is tertiary carbocation. In this case, it is highly stable. It is stable. We have taken, this is alkyl bromide, nothing but tertiary butyl bromide. This is what we can say is the first step of the reaction. Coming to the second step, what is second step is the nucleophile attack on the carbocation. The step 2, whatever the nucleophile is there, that will attack the carbocation. It's a positively charged carbocation. Carbon with positive charge is carbocation, and the nucleophile, whatever nucleophile we are taking water in this reaction, having oxygen, 2 lone pair of electrons, and one of the lone pair of electron will fall onto this carbocation, forms the first initial product is nothing but this positive charge will be transferred to oxygen. There will be oxygen forms, there is a triple bond, 3 bonds with oxygen will be present in this case. That's why oxygen will acquire positive charge, and after this it will undergo elimination process of a proton. That means you will get a final product. What is the final product is? Alcohol. So here CH3. Like we said earlier, H plus ion removed. Here also H plus ion got removed. This is the case in which oxygen is having 2 pairs of electrons. So on the second step, what happened? The nucleophile reacts rapidly. This is a fast reaction. But in the first step, that process is a slow process. First step, the process is nothing but slow process. Attack of nucleophile in the second step with the carbocation formed in the first step, which is in the second step is a fast step. From the above observations that the rate of Sn1 reaction depends only upon the concentration of RX. RX means alkyl halide. We know that the first step is slow. This we will call it as a rate determining step. Simply in a shortcut manner we can call it as RDS. Because nucleophile is not involved in this rate determining step, its concentration has no effect on the rate of reaction. So nucleophile is not there in the rate equation. Okay. So if you look at the reaction coordinate diagram, then you will come to know. You'll be able to see why increasing the rate of the second step will not make S1 reaction go any faster. Okay, we will see that one. Okay, let us see this whatever we said about the energy diagram, energy profile diagram. In this, the coordinate diagram, whatever the progress of the reaction on x-axis we have taken x-axis, and delta G0 free energy we have taken on the y-axis. We have different peaks are there. There are about 3 peaks came mainly. The first peak we can call, that is nothing but the alkyl halide, okay, that is started involving into the reaction, and in this carbocation is formed in the slow step of Sn1 reaction, because tertiary carbocation is more stable than, therefore easy to form than a secondary carbocation, which in turn is more stable to form than primary carbocation. So what we understand from this one is tertiary alkyl halides are more reactive than secondary alkyl halides, which in turn more reactive than primary alkyl halides in Sn1 reaction. So this is the peak, first peak, whatever we obtained, that is the alkyl halide reacts, undergo cleavage, forms carbocation, that is stable carbocation, its free energy value is less, means it is stable. And after that it starts joining with the halogen, halide. Attack is water, halogen and water. Halogen is separated out and water is nucleophile. It starts coming onto the carbocation. That time energy here raised up to this level. Then after this carbocation changed to oxonium ion where energy is less. After that, leaving this H plus ion, there is some energy again increased. Here there is another one. So after that we got final product with stability with lower energy values. Okay. Now we understand relative rates of alkyl halides in Sn1 reaction. Relative rates of alkyl halides in Sn1 reaction. As you know, tertiary alkyl halides, from this example we can understand this tertiary alkyl halides are said to be more reactive than secondary alkyl halides, which are in turn more reactive than primary alkyl halides. After that we discussed about the alkyl halide, methyl halides. So actually primary carbocation and methyl carbocation are also unstable in this case, that primary RX and CH3X do not undergo Sn1 reactions. So these are quite unstable. They do not give this reaction, give Sn1 reaction without any condition. Okay. The very slow reaction reported from ethyl bromide and methyl bromide in observations, in the different kinds of observations. Okay, we will move to the next one. Okay, let us see. In this, we have taken alkyl halide, the positively charged carbon of carbocation here, whatever is there. This is said to be sp2 hybridized. As you know that it is sp2 hybridized, and the three bonds connected to this carbon are in the same plane. In the second step of the Sn1 reaction, what we did is nucleophile can approach either side of the carbocation. So this is what we have depicted here, represented, and there are two types of attacks we have shown. One is front side attack, one is back side attack of the carbocation attached halogen side. So towards the halogen, one type of attack, opposite to the halogen, another type of attack. So there is no discussion about halogen now in the case of carbocation. Very simple. This is one direction, this is another direction, and we have taken nucleophile. So let us see. The Sn1 reaction of the alkyl halide in which leaving group is attached to the chirality center. This is chirality center. Chirality center. Okay. There are some isomers also positive. Attack of the nucleophile on one side of the planar carbocation forms stereoisomers, and attack of the other side produces the other isomers. So here we obtain two types of isomers. One is called as inverted configuration, means whatever alkyl halide you have taken, as it is the opposite to that one, the structure is obtained like Sn2 mechanism. But second case, if you observe, we got retention of configuration as it is similar to that of configuration of alkyl halide. We got the product alcohol. Okay, so this is what one of the most interesting thing in this case. We will take different examples. Even if you take a different example like alkyl halide with chiral centers, then that can also be represented. We will see now. So let us see some examples here for Sn1 reaction. As we discussed, the Sn1 reaction of an alkyl halide, which is the leaving group, attached to a chirality. Here, this Br is a leaving group attached to the chirality center, leads to the formation of two stereoisomers. This is chiral center. So there are two stereoisomers are formed. One is inverted configuration, another one is called detention of configuration. Okay. So let us observe. This is the model. This is called, as you know, like the same. Here we got this. We will call it as retention of configuration. Retended. This we can say it is inverted. Inverted. This is the model example. We will take a chemical compound in the second example. It is S2-bromobutane with water. Assume this is bromobutane. Here I am taking bromine. Okay. So your products will be HBr only. Let us see. S2-bromobutane I have taken. I got two products. Let me mixer. R2-butanol, S2-butanol, it ended here. Okay. So let us observe. In this case, this is original alkyl halide structure. This is inverted one. This is inverted. After that, this one came after the attack of nucleophile. Retention of configuration came also. So it's a mixture of 50-50% of this 2-butanol or S2-butanol obtained. See one more example we have, that is Cis1 bromo 4-methyl cyclohexane. This is Cis1 bromo 4-methyl cyclohexane. I can say one thing. The diagram whatever we are showing in the last equation, the compound name is Cis1 bromo 4-methyl cyclohexane. So in this, when cis bromo 1-bromo 4-methyl cyclohexane undergoes this Sn1 mechanism, there is easy method, easier way of visualizing this Sn1 mechanism is with this cyclic compound obtained. Okay, so in this compound we got 4-methyl cyclohexanol. This is 4-methyl cyclohexanol we got here. This is R configuration, this is S configuration, this is R configuration, this is S configuration. So it's a mixture of R and S configurations. So this is also 4-methyl cyclohexanol. You observe the shaded portion is nothing but the atom which is present towards observer and dotted one away from the observer. So backside of this hydrogen bond, this carbon OH bond is there. So here also the same thing. That means when backside attack happened, we will get inverted configuration. This is nothing but inverted configuration. When front side attack happened, we will get this type of product called as retention of configuration. The configuration is retained. So you can understand like this. Although one might expect that equal amounts of two isomers would form in Sn1 reaction, but greater amount of inverted product is obtained in most of the cases. Why? Because that is stable. Typically 50 to 70% of the product of Sn1 reaction is inverted product. If the reaction leads to the formation of equal amounts of two products, reaction is said to take place with complete racemization, and when more of the inverted product is formed, the reaction is said to take place with the partial racemization. So we can understand that in this inverted configuration percentage is more means that we will call it as partial racemization, and if 50-50% obtained means then we can call it as complete racemization of the reaction. Okay. Let us see this one's complication in Sn1 reaction mechanism product. When the stable alcohol forms, then there should be another mechanism involved, rearrangement involved in this carbocation, that is called as 1,2 methyl shift. Let us see, when we take this type of example, that means neopentyl halides, if you take this CH3, CH2, I am taking iodine is a good leaving group. In this iodine I am taking. So I can call this one as 2,2 dimethyl iodide. So in saying like that, it is very difficult to understand this one. So we can call this is neopentyl halide. Okay. So in this, I am taking first step of the Sn mechanism. Step 1. What will happen in step 1? As you know, in the step 1, there will be formation of carbocation. So this cleavage happened, heterolytic cleavage. After that, I got this product, that is CH3, and this carbon, whatever is there, CH2 carbon, that has became positive. This is carbocation. You can call this is primary carbocation. Primary carbocation. As you all know that primary carbocation is not stable. Then in this type of cases it will undergo rearrangement. It will undergo rearrangement to tertiary carbocation. That rearrangement we will call it as 1,2 methyl shift. 1,2 methyl shift. Here methyl group will go towards this carbocation, and whatever this hydrogen is there, that will come to this point. Okay, then see how the product will be. It is CH3, it is also CH3. You can write this one is hydrogen here. This will become positive, and here this carbon is got satisfied with a methyl group. Okay, so this is what I can call, this is a tertiary carbocation which is stable. So let us observe, there is a shifting happened. This bond with methyl group went along with this electrons towards the carbocation. So this is got tertiary carbocation more stable. Now we got more stable tertiary carbocation in the first step itself. By taking neopentyl iodide. Let us see the second one. Second one, as you know, this is nothing but attack of nucleophile. Now, nucleophile can easily attack this carbocation which is stable to give stable alcohol. That is CH3. We have positively charged here, CH2, CH3. Now, what is the step 2? What is step 2? Step 2 is nothing but attack of nucleophile. Attack of nucleophile, that is OH minus. So then we'll get the product. First we have CH3. We have CH3 here. This one will become OH after the removal of H plus from water. Okay. So this is CH2. This is CH3. Want to show with water, then one more step will come. Okay. Finally we got a product, that is tertiary alcohol. What is the name of the compound? Let us see. This is 1, 2, 3, 4. In this second carbon we have methyl is there. This is 2-methyl. It's nothing but 2-methyl but 2-1 is a stable compound obtained in this example. So we have such different kinds of interesting aspects are there in this Sn1 mechanism. Let us see one more thing. In this mechanism, finally what we understand is nothing but we have a possibility of racemization. There is a possibility of getting inverted configuration along with the retention of configuration. So in this Sn1, we can believe that one thing happened, that is the order of reaction is 1, and here we understand one more thing, that in Sn1 reaction we have the partial racemization of the configuration. Racemization also takes place, and mainly the tertiary alkyl halides are said to be, alkyl halides are said to be more reactive in this Sn1 reaction. Nucleophile can be a poor nucleophile in this mechanism. That can be Sn1 mechanism. These are the main important trials of Sn1 reaction mechanism. We will see the further developments in the mechanisms in the next session.